Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss electric braking in DC motors. Friction or mechanical braking imposes difficulties to achieve a smooth stop due to the condition of braking surface. Electric braking in this regard is of paramount importance and it allows us eliminate these issues of friction. So electric braking is of following three types: rheostat or dynamic braking, plugging or reverse current braking, and the last type is the regenerative braking. Rheostat or dynamic braking can be achieved by connecting a series variable resistance with the armature winding. So this is our motor and we have applied a voltage at the armature terminals and this motor is running. When we intend to stop this motor, first of all, we will remove this connected supply, and after that, this motor will behave as a generator because due to inertia, its armature will keep on running. At that instant, if we connect a variable resistance in series with this armature, then all of the stored energy in this armature will be dissipated in this series resistance. So whenever a motor is running uh, after the connection of the input DC supply, then the applied electrical energy to the motor is equivalent to the produced kinetic energy. Similarly, when we remove this power supply from the armature of the DC motor, then the stored kinetic energy due to inertia in the motor will be equivalent to the stored electrical energy in this motor. So when we connect a series resistance with this armature, then the stored electrical energy will be dissipated in this resistance and that electrical energy will be consumed quickly, right, in this circuit. As soon as all the electrical energy stored in the windings of this armature is dissipated in this resistance, all the kinetic energy available in this armature will also be consumed. So this armature will tend to stop quickly as soon as the stored electrical energy is dissipated in this resistance and there is no more electrical energy in this armature winding. So this is one way of stopping the motor quickly by using this resistance, and this method doesn't require any friction mechanism or mechanical brake, right? So in friction or mechanical braking system, we all know that the braking surface undergoes wear and tear and the brake leathers also undergo wear and tear in a quick span of time, and after some time we need to change the brake leathers. So this thing is eliminated in electric braking, right? So electric braking is more sophisticated and it is more durable, right? So in this case, when we have removed the applied electric supply to the motor and we have connected a series resistance with the armature current will be equal to EB divided by R plus RA, because in that case the induced EMF in the armature will be responsible for the current and that current will be flowing through the armature resistance plus this series resistance. So armature current will be equal to EB divided by R plus RA, and we all know that EB back EMF is equal to phi Zn multiplied by P divided by A, and here we have R plus RA. So this is the armature current at the instant of braking. Braking torque TB is equal to 1 over 2 pi phi ZIA multiplied by P over A. This is the expression which we discussed in one of our previous lectures, which I can show you over here. So this is our armature torque, right? And armature torque can be written as this after these simplification steps. So the braking torque must be equal to the armature torque to overcome the armature kinetic energy, right? So braking torque must be equal to the armature torque if we want the motor to stop, right? So braking torque must overcome the armature torque, right? Then the motor will stop. So this braking torque can be written as this expression, and we can substitute the value of IA in this expression, and we will get this new formula. And in this formula, all of the terms are constant apart from the flux and the speed. So we have phi square multiplied by n and this constant term. So this is the speed, and when we have arranged such mechanism, the motor speed will start decreasing, and as soon as the motor starts decelerating, its speed will decrease and its braking torque will also decrease, right? And when the motor stops, the RPM of the motor will be equal to zero, and at that instant, the braking torque will also be equal to zero. So, braking torque is directly proportional to the motor speed, and when the motor is at maximum RPM, the braking torque will be maximum, and when the motor is decelerating, the braking torque will also be reducing. So this is the first method of electric braking, and it was called rheostat or dynamic braking. The second method is called plugging or reverse current braking, and in this method we will reverse the terminals of the armature, right? So in this method, connections to the armature are reversed so that motor tends to run in the opposite direction. Suppose the initial connection of the armature was this terminal was connected with this carbon brush, and this top terminal was connected to the upper end of the bus bar, and that was the applied voltage. At the instant of braking, we will reverse the connections to the armature such that this upper carbon brush will be connected to the lower end of the uh, voltage supply, and this lower carbon brush will be connected to the upper side of this voltage supply, and we will use a variable resistor in series with the armature winding in this method, and I will tell you later the need of these variable resistance. So now in this case, the armature current will be equal to applied voltage plus EB divided by R plus RA, and in this mechanism we will no longer be removing the connected supply, so that connected applied supply will remain connected with the motor, but these terminals will be reversed so that now in this case the motor will experience a torque which will be applied in the opposite direction. So this motor will tend to stop quickly, right? So in that case, armature current will be equal to V plus EB divided by R plus RA, and that will be equal to V divided by R plus RA plus EB divided by R plus RA. So we can substitute the value of back EMF in this expression. So it will be equal to 1 divided by R plus RA multiplied by N phi Z multiplied by P over A. So braking torque expression is written as the same, and it is equal to 1 by 2 by phi Z IA multiplied by P over A, and IA is equal to this expression. So this expression can be substituted over here, and this is the braking torque expression for the plugging or reverse current braking. And after the derivation, we will get K2 multiplied by phi as the first expression, and K3 multiplied by phi square N as the second expression. So if our flux is constant, which is true in case of shunt motors, then we can write K4 plus K5N, right? In series motors, field current is variable, so flux is also variable, but in shunt motors, field current is constant, so flux is also constant. And in this case, we can see that the braking torque is equal to constant term plus K5 times N. So in this case, even if the speed of the motor is zero, there will be some braking torque which is present in the motor. So even if the motor is stationary, braking torque is present. So if the motor is stationary, it will be difficult to run the motor, okay, uh, because braking torque is already present in the motor. So when motor terminals are reversed, EB and V have same polarity, so resistance R is used to limit the current. So this is the reason why we have connected this series resistance with the armature winding, because in principle IA is equal to V minus EB divided by RA. This is the expression for the motor, right? IA is equal to V minus EB divided by RA. But when we reverse the terminals of the armature, IA will be equal to V plus EB divided by RA. So we know that RA is extremely small because the winding, armature winding, is made of copper material, and copper is a good conductor of electricity. So RA is small and IA can grow much higher because these two voltages are in the same direction and they will tend to increase this armature current. So in order to limit this armature current, we must use a series resistance over here so that the armature winding stays safe and it doesn't undergo damages. So that is all about our second type of braking, which is called plugging or reverse current braking. Now this is the final type of the electric braking, and this is called regenerative braking. And it is an energy recovery mechanism that slows a vehicle by converting its kinetic energy into a form that can be either used immediately or stored until needed. So in this mechanism, whenever a motor is running, we want to stop that motor. First of all, we will disconnect the supply, and after disconnecting the applied voltage, that motor will be running due to inertia, and in that case, that motor will be acting as a generator. So if we dissipate or if we store the produced electrical energy uh, from that generator, or we consume that electrical energy by some means, then the kinetic energy of the motor will also be consumed quickly and the motor will tend to stop immediately. So this method is used in conjunction with friction brake, and it is required knowledge of braking distance. And during regenerative braking, motor acts as a generator supplying electricity to the grid, for example, in the case of electric trains. So, for example, when an electric train is running and we want to stop that train, we can turn off the supply to the train, and the train will behave as a generator, and we can use the electrical energy from the train to be supplied to the grid, right? So that energy can be supplied to the grid, and that electricity from the grid can be used by the consumers. And we must know the knowledge of braking distance, right? Because if we want to stop the train quickly and we don't have a sufficient distance to cover, then that regenerative braking must be applied far before the braking point, right? So this regenerative braking must be applied far more early, right? And during regenerative braking, motor acts as a generator supplying electricity to the grid, and it is used in conjunction with the friction brake. And the friction brake, we all know that we will connect a resistance in series with the armature winding after removing the voltage supply. So that is one mechanism of dissipating all the kinetic energy. And similarly, we will also be using the produced electrical energy by transferring it to the grid. So the consumers connected to the grid can use that electricity, and alternatively, we can also store that generated electrical energy in batteries. So that is all about our today's lecture on electric braking, and I hope you have understood the concept which was intended to be discussed in detail. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.